All right, so now we're going to discuss convergence analysis on manifolds. Okay, so the notion of convergence on manifolds is a relatively straightforward generalization of the vector space case. All right, so the notion of convergence is a straightforward generalization of the Rn case. All right, so let's say you consider a sequence of iterates, okay, say xk. K goes from 0 and so on, of points on a manifold. M. Okay. This sequence is said to be convergent. Okay, if there exists a chart, okay, with sort of an open set where the domain definition of the chart is, and the function of M, and a point, let's say x star, which is in the domain of the chart, okay, and a k greater than 0, okay, such that xk is in U for all k greater than equal to this critical value of big K, and if you apply the coordinate function to the xk's, right, you look at that, okay, so k goes from big K plus 1 onwards, okay, converges to the coordinate function applied to this candidate limiting point x star, okay, in Rn basically, right? Yep. Okay, so the point, of course, is that if you apply the coordinate chart to the sequence of points, it's like, and if all those points are in this coordinate chart, then this is just some n-tuple numbers, and this is again some n-tuple numbers. So you can look at the convergence. It's like of basically sequences. It's like in Rn, it's like to some potential limiting point, and that's one way to set this up. Okay. Okay. So yes. Okay. And then the limit then is the pre-image, if you will. It's like of the limit. Okay. So the limit of the convergent sequence and is given by the inverse of the chart applied to the limit of the limit of the image, it's like of these points in Rn, right? Okay, so so the chart applied to, it's like the xk's, it's like for k large enough, it's like is an n-tuple, it's like you can look at the limit in the usual sense of Rn, and then that gives you some limiting, it's like point in Rn, and then you can look at the inverse of that, and that will be the limit of your sequence. It's like of points. It's like on the manifold. Okay. And then the point is that every convergent every convergent sequence of a Hausdorff manifold has one and only one limit point. Okay, so I should remark that this condition that it is Hausdorff is absolutely critical. Okay, so let me just state that. So the remark is that the Hausdorff assumption is critical. Okay, and then it's possible to have sort of multiple sort of limit points sort of for non-Hausdorff topologies. And in particular, it's like the book goes on to present an example. It's like of a non-Hausdorff quotient manifold. It's like with a convergent sequence which has more than one limit. Okay, so I'm not going to discuss that here, but again, it's important to realize that this assumption that you're on a Hausdorff manifold is critical for there to be a limit and for there to be a unique limit. Okay, so we've we've defined this. It's like in the notion of a sort of in terms of the coordinate charts. It's like equivalently, you could also sort of talk about this more compactly by just talking about the sort of the manifold topology, basically, right? Because I guess the main point, of course, is that the notion of convergence is really just sort of defined. It's like in terms of the topology you've chosen, and this way we've done it in terms of coordinate charts is sort of a roundabout way of saying that we're looking at convergence as like on a manifold of respective manifold topology, which is induced by the atlas, right? So an equivalent sort of in more concise definition is that a sequence on a manifold is convergent if it is convergent with respect to the manifold topology. Okay, so this is basically saying that there is a point x star, right, such that every neighborhood of x star, okay, contains all but finitely many points in the sequence. Of the sequence. Okay. All right. So to allow for the possibility, it's like that you have sort of more than one limit. It's like we're going to talk about sort of accumulation points and limit sets. Okay, so given a sequence, xk, right, we say that x is an accumulation point. Okay, or a limit point. Of the sequence. Okay, if there exists a subsequence let's call that xjk, such that that converges to x. And then the set of all accumulation points is called the limit set. Of the sequence. Okay. All right. So again, this is sort of just a brief recap, if you will. It's like the relevant notions of convergence on a manifold, and then the next thing we're going to talk about is how to go about showing that the algorithm, the line search algorithm we had developed, the second manifolds, is convergent in this sense. So let me just stop here for a minute.